This is a login screen to the ThunderScan SaaS solution. Once we proceed with the login, we are presented with a dashboard that has several finished scans listed. The dashboard offers an easy way of scan management through scan searches, scan filtering by scan status, risk levels, sorting by any of the columns shown here. You can also delete the scans or stop any currently running scans. You can also immediately review the results of the scan through scan details or the summary of a scan. You can review the languages involved in any of the scans as they are shown in the dashboard. The dashboard also has an applications feature. Applications represent the grouping of scans for the purpose of scan history and delta. For example, in this application called Test App here, we have a scan history of 2 scans. We can see the latest delta between those 2 scans. For example, there were 34 fixed vulnerabilities of high risk. There are 14 vulnerability types. In case some vulnerabilities were introduced, they would show as new, and these risks would also reflect that. We can see the languages involved in the project and the total number of scans against the application. Total vulnerabilities over time chart will pick up the last 20 scans and show all the ups and downs with introducing or mitigating vulnerabilities. The bar charts here will show compliance violations in the latest scan as well as the risks involved in the latest scan. From here, we can also trigger a new scan against the application, as the application also stores all the configuration for the scan and the target data. For example, if this was a Git repository, triggering a new scan would reclone the repository and scan it and add it to the scan history. When creating a new scan, we have 3 configuration steps or options. The first one contains the following parameters. We can assign it a parent application. This is not a required parameter, but in order to have a scan history of a certain application, a scan should be assigned a parent application. We have a scan name and we have a language selection. A scan can be performed with multiple languages selected, or ThunderScan can automatically recognize all the languages in the project by using the auto language recognition option. We chose C# for this scan, and now we need to set the new target source. We have uploads, which are the zip archives of the source code. We have Git repositories, where you can specify a repository URL, be it the HTTPS or an SSH repository, doesn't matter. And we can also optionally specify a branch for the scan. We also have SVN, Team Foundation Server Version Control, Amazon S3 bucket objects, and local paths as scanning targets. We are going to select one of the already uploaded projects for this scan, and we can proceed to advanced options of the scan. The scan can be started with only the basic options set, but we are going to review the advanced options as well. On the left side here, we can see all the vulnerability types that are supported for the analysis. We can choose to exclude any of these vulnerability types, and they won't be shown in final results or any of the exported reports. On the right side here, we can see tracked input variables. Tracked input variables represent input sources, for example, any function or a property that might take user input from some source, be it the HTTP request, a parameter, a command line argument, or a file path. We can add new tracked input variables, or we can exclude some of the default exposed ones here. On the bottom, we have custom filtering functions and custom vulnerability rules. Custom filtering functions represent any function that might sanitize the user input in a non-standard way. For example, When mitigating cross-site scripting vulnerabilities, you can choose to encode the input during the output phase when reflecting it in the response by using default functions in languages such as default encoders, or you can write your own custom filtering functions that might for example, replace some special characters, and you should let ThunderScan know the name of that function and the type of a vulnerability that function mitigates in order to avoid false positive results. We also have custom vulnerability rules. These represent function signatures for sync functions in frameworks that we might not support, where you can define a type of a vulnerability that function will cause if the parameters are passed unsanitized into its parameters. In the last options here, we can see the actual depth of the scan in terms of tracking the user input through function calls and variable copying. We can see that we can select any automatic issue submission triggers for Jira or Azure DevOps work items. We can choose to include filtered findings in the scan. For example, if the user input has passed through some filtering function, by default it won't be reported in the results, but we can choose to include those results. A deep input discovery option refers to a discovery of wrapped input functions that might be difficult to detect in some projects, and that option is selected by default to produce more results. Ignore stored false positive results represents an option to ignore any results that were marked false positives in previous scans over the same source code base. Once we start the scan, we are presented with the summary of the scan. The results will appear shortly. In the scan summary, we can see the total vulnerabilities that were found, the scanning duration, the total files or total lines that were analyzed in the scan, and we can also see all the vulnerability types that were found with counts for each of the vulnerability types. If we scroll down, we can also see any violations to compliance standards that are supported in ThunderScan with exact articles and counts of how many violations there are. If we proceed to the details of the scan, we can see here a language drop-down menu, which will, in case of multi-language scans, will show all the languages involved in the scan, and you can review the results per language instead of having them merged together in one tree view. By opening any of the vulnerability types, we can review individual vulnerabilities that are present for that type. In individual vulnerabilities, we have all the information such as the actual function that caused the vulnerability, how that function can be abused, in this case to perform a SQL injection attack. We can see what the input variable or the input source was, what was the sync file that caused the vulnerability, a vulnerability description, any violations under which that vulnerability might fall under, mitigation recommendations with references to external resources. We can also see a CWE entry for that vulnerability, which is clickable and leads to mitre.org definition of that CWE. We can choose to change the risk of the vulnerability. If we consider a certain individual vulnerability to be a different risk than what is reported, we can change it. We can also change the risks for the entire group of vulnerability. For example, for this SQL injection type, we can change the risk to medium if we want. At any point, vulnerability can be marked as a false positive result, and as previously shown, you can choose to exclude those results from future scans over the same source code base. From here you can also submit a ticket to one of the supported issue tracking systems. If Jira or Azure DevOps are configured, all the Jira projects will be shown here with issue types, with an option for adding an additional comment to the ticket. The ticket will contain all the information necessary to track down and fix the vulnerability. To further analyze the vulnerability, we have a data flow of function calls and user input flow. By clicking on any of the items, we are led to the full source code highlighting. We can see that this vulnerability originated from the text email, text variable. We can see it was passed on further to the get security question and answer function as the email parameter, and we can see that that email parameter was used to concatenate to a string in an insecure manner without sanitization, and that SQL variable was finally passed on to the SQL data adapter function that caused the vulnerability. This explanation that I just gave is also available in the summary of that vulnerability. Summary represents a high-level description of the data flow, so we can see that the tainted input was received in line that and that of file that and that, passed further on until it was finally passed unsanitized into a sensitive sync function that caused the high-risk SQL injection vulnerability. With creating reports, we have 4 available formats, which are HTML, PDF, XML, and JSON formats. For each of these formats, we have several report types, which are defense code, default format, and compliance formats such as OWASP Top 10, SAN CW Top 25, NIST, PCI DSS, HIPAA, and HITRUST. If we generate a defense code default form type in an HTML format, we can see all the results in the report. By clicking on any of the results, we can see all the details that we saw in the web user interface.